Chaos is but unperceived order. It is a word indicating the limitations of the human mind and the paucity of observational facts. The words chaos, accidental, chance, unpredictable are conveniences behind which we hide our ignorance.
The Interplanetary Podcast. The exploration of space for the benefit of all mankind. Your hosts here in London, Matthew Russell and Jamie Franklin.
Ooh, yeah, baby space.
Matt, was that Harlow Shapley or Shapley?
I think it must be Shapley.
I tell you what, Matt, either way, what a quote that is.
It's his birthday today. Happy birthday.
Happy
obviously.
birthday.
He died just as the Apollo missions died back in 1972. He was pretty old.
He had a good innings.
He had a good innings and did some remarkable things, as we're about to hear.
Here we go.
Because he's going to be our space personality of the week, for it's his birthday.
Matt, is that a new feature? Space
Is it?
personality.
Well, no, I like to think of it as being a kind of subset of Astronaut of the Week, or
Yeah, it's kind of
it's that kind of thing, isn't it?
It's of a similar vein.
Yeah, Harlow Shapley. He was an American scientist and head of the Harvard College Observatory, born on a farm in Nashville, Missouri.
Well, I was just going to say, he dropped out of school with only the equivalent of a fifth grade education, which, Matt, should be inspiring to our younger listeners. It doesn't always, I'm not saying don't study, but it doesn't always matter about results, does it, Matt?
No, because and get this, the most incredible part of this story is that Shapley wanted to be a journalist, and he was actually a very, very good writer and wrote lots of books, and that's why his quotes are so good. But he went to study journalism in Missouri, but the School of Journalism wasn't going to be opened in time and was postponed for a year. So he just went through the directory and said, what am I going to study? And he just literally started going through alphabetically, rejected archaeology, which he said he couldn't pronounce, and so chose astronomy.
I love that, but bloody, what a way to choose your course. Yeah, what do you fancy doing? I don't know, just read them out. Start from the top. What have we got? Archaeology. No, can't say that. Astrology? Yeah, go on then. Oh no, wait, I said you see what I did there, Matt? I said astrology.
Imagine if he'd accidentally done that.
Oh God.
I'm assuming, hopefully, it wasn't a course.
In line with Mars, today you will meet someone who's wearing red. Oh, do you know what I mean? Do you know what I mean, Matt?
The worst. I've got quite a few friends who believe in astrology. That's the distressing thing.
I don't understand it. It's
understand.
Really silly, isn't it?
Well, it's the human's propensity to see agency in coincidence. Let's move on.
Let's move on.
He got a fellowship to Princeton University to work under Henry Norris Russell.
Any relation?
Uncle Henry.
Yeah.
Yes, he became a bit of a star quite quickly, and his 1914 PhD thesis on the orbits of 90 eclipsing binaries created a whole new branch of double star astronomy in one single stroke.
That's my kind of stroke.
We're going to talk about Henry Norris Russell a bit later on in our special feature.
Yeah, we are.
Mm-hmm.
Well, Matt, he used RR Lyrae stars to correctly estimate the size of the Milky Way galaxy and the sun's position within it by using parallax. You know what parallax is, don't you, Matt?
Yeah, it's a bit like when you're looking at your speedometer from an angle and you think that you're only doing 60 miles an hour, but really you're doing 80 because you're just not looking at it straight on. Well, that's my excuse to the police officer that pulled me over the other day.
Yeah. I promise I was just looking at it from the right.
But then I suppose I shouldn't have been driving from the passenger seat.
That was your error.
Yeah, he wasn't impressed by either. So what's funny is that Shapley was part of what's known as the Great Debate, or the Shapley-Curtis debate, which Shapley was wrong, actually. He sort of said that the Milky Way was just a spiral nebulae, and that the whole of the Milky Way was the universe. But Curtis basically said no, that the Milky Way was an island universe amongst many. And of course, he was right.
Yeah, he was right.
He was right, and it essentially started that whole understanding that there was more than one galaxy and that there was multi galaxies all over the place.
Must have been satisfying when he was proved right.
Yeah, it must have been very satisfying indeed. Well, Hubble was, of course, involved, and Shapley was very critical of Hubble. Basically, Hubble wrote him a letter and said, "Why are you being so mean? Here's the evidence that I've got." And Shapley, being a good scientist, said, "Here is the letter that destroyed my universe." And it went on to fundamentally change the whole scientific view of the universe. So,
that's incredible.
Yeah,
well, at least he admitted it.
Mm-hmm. He's done some other cool things, like in 1953, he was the person that proposed that there would be a liquid water belt, i.e. the Goldilocks zone, i.e. the habitable zone. So that's kind of his idea, the habitable zone. He put the S in UNESCO, i.e. the scientific bit of UNESCO.
Ah, okay.
Mm-hmm. And his son, one of his 5 children, Lloyd, won a Nobel Prize in economics in 2012.
Bloody hell. Runs in the family.
But weirdly, I'd only heard his name, Shapley, because of the catalogue of galaxies. So when you're sort of looking up in the night sky and using those apps to try and find galaxies you can take photos of and stuff, the Shapley catalogue comes up, the Shapley Ames catalogue of bright galaxies in 1932, 1,249.
Well, Matt, what about the Shapley supercluster or Shapley concentration?
Yeah.
Or Matt, you probably know it as the SCI 124, don't you?
Oh, big
You're
time.
such a geek. The largest concentration of galaxies in our nearby universe that forms a gravitationally interacting unit, thereby pulling itself together instead of expanding with the universe. Check that out.
I love those facts because obviously we're always going on about how the universe is expanding, but of course certain parts aren't. If there's enough gravity, they will be collapsing in on themselves.
Correct.
But eventually they will still be ripped apart by the expansion of the universe.
Well, Matt, you know that he was part of the Great Debate.
You know I'm going to cut that out. And I knew exactly the moment you said debate, I knew exactly where you were going.
So predictable. Oh, dear. Hey, Matt.
Yes.
You know what everyone's favourite section of the show is?
Go on, hit me. What's everyone's favourite section of the show?
Well, apart from the moment that we say, well, we better let you go now. I think it's Space Word of the Week.
Space Word of the Week! I agree.
That is downloadable as a ringtone. Now, Matt, you're going to have to pronounce this one. I think it's nucleosynthesis. Am I right?
You certainly are. And it's not by a Roland or Yamaha or any other reputable synthesizer company.
No, don't be silly, Matt. It's the process that creates new atomic nuclei from pre-existing nucleons, primarily protons and neutrons. I mean, any idiot knows that.
Well, basically, it's how stuff is made. Like all the matter in the universe is kind of made like that. But there's quite a few processes, and the reason why I brought it up is because we're going to talk about the sun in a bit.
We are going to talk about the sun
in great depth.
We were sort of talking about what we should do on this show, and I got a bit excited about the sun, didn't I?
You did, and I think every month we should talk about a space thing to remind ourselves about why we want to go to space in the first place.
Yeah, I mean, it's all very well us gabbing on about rockets and SpaceX, whatever. The reason that we do that is because of the majesty of the universe.
And we send
now you can quote me on that, Matt. Quote me on that.
The majesty.
I think I should be the quote for next week.
Okay, we'll do that. We'll do a quote
from J.R. Franklin.
Is it J.R.
Born in 1979.
Or is it J.R.
Brilliant.
Hartley?
Okay,
right. This is incredible. within 3 minutes after the Big Bang,
Yeah.
the first nuclei are starting to be formed. 17 minutes later, the universe had cooled to a point where that process was over. So it's only in the first 20 minutes this is all happening.
It's ridiculous.
So only the really sort of fast and easy ones. So after that, 20 minutes, 75% hydrogen and 24% helium, and a few trace elements of things like lithium and isotopes of hydrogen, of course. So and pretty much that's where the universe is today. However, there's other ways to make more. It'd be really boring universe if it was just hydrogen and helium and a bit of lithium.
It would.
So luckily, we have stellar nucleosynthesis, which makes carbon and iron and heavier stuff via a thing called S process. Then we've got explosive nucleosynthesis, so things like supernova that generate even heavier stuff. And then neutron-star collisions that might even create things like gold and heavier stuff still. And even things like the black hole accretion disk is such a chaotic place. You get things smashing into each other and creating larger and larger nuclei and stuff and elements. It's just how the elements are made.
What about Noel Gallagher, Matt? Was there any truth in the champagne supernova?
No, I don't think that made any elements apart from idioticus.
Okay. All right, move on.
Cosmic ray spallation or spallation. Basically, cosmic rays are travelling so fast and these balls of nuclei like hurtling through the universe, bashing into things and possibly making lithium, beryllium and pretty much all of helium-3.
Do you know, Matt, once when I was at school, my uncle, when I was quite young, my uncle taught me via a song the periodic table. And I don't really remember it, but I might practice it and try and sing it for next week's show.
Okay, we'll have a little sing.
But Matt, imagine my upset as I spent weeks learning that song for my science exams, only to find a copy of the periodic table on our desks during the exams. True story, that. Yeah, gutted.
That's what's known as poor exam technique.
Still, Matt, I mean, all of the girls that I got from singing that song, eh? The periodic table song. Imagine me with a bevy of beauties around my arms.
Yeah.
It didn't happen, Matt.
Well, if there was, it would just been because of your sharp good looks.
Well, I mean, there's no debate there. There's no great debate there. Matt, so our space science thing of the week...
Is that a weekly thing, space science thing of the week?
Well, it's going to be now.
Okay. What is it?
Space science thing of the week. It's the sun, of course.
Oh.
Now, Matt, your first question to me was, how was she born?
How was she born?
Well, let me tell you, Matt. About 4.7 billion years ago, a giant cloud of gas was starting to swirl. Mostly hydrogen, as we know, but also some helium and tiny amounts of metals like 1% oxygen, 0.3% carbon, 0.2% neon, which is my favourite. And
I think that's a surprising one, neon.
Oh, yeah, it is, isn't it? And iron was 0.2%. But incredibly, the hydrogen and most of the helium would have been made about 9 billion years earlier, Matt. In the first 20 seconds of the universe, as you said, that is ridiculous.
Yeah. Do you know where the rest of the stuff came from?
Oh, I'm guessing it's stellar nucleosynthesis.
It certainly is. And that was from an older generation of stars, long extinct, blown into the universe as the stars shed their skin, or exploded as supernovae.
Life breeds life, Matt.
Life breeds life. And that gave that cloud of gas a very unique property, which we can see in the sun. But you carry on. Tell me the rest.
Well, here we go. The cloud started to spin gently from a disturbance, maybe a shockwave from another dying star. And now that massive cloud had a tiny, tiny spin. And the system started its collapse under gravity. and it all started spinning faster and faster, like an ice skater, Matt, with the arms out. When they pull their arms in to spin faster and faster, that's kind of a similar vibe, right? And over the next 50 million years, the gravity pulled and pulled tighter and tighter into this cloud of gas. And under its intense pressure, it got hotter and hotter, causing the gas to ionize into a soup of atomic cores, protons, and neutrons, stripped of their electrons, Matt. I mean, you know this. But it got hotter and denser still. And some of these cores would smash into each other and cause, Matt, what I said last week, nuclear fusion. That's what I learned about last week. And Matt, I'm just expanding on my point. See what I did there?
What's great about this nuclear fusion? So you've got this huge cloud spinning, getting hotter, denser, and it's all collapsing in. Gravity's really bashing it around. But this nuclear fusion then supplies a force that kind of balances it out. So as it gets denser, the nuclear fusion gets more and more and more, and as it gets denser, it gets more and more and more. But then suddenly, you've got this outward pressure from the nuclear fusion that balances out the sort of collapse from gravity, and you're left with this massive ball of plasma at the centre of the once protostellar gas cloud. And do you know what that ball of plasma is called?
No.
It's called the sun.
Oh, simple as that.
It's as simple as that. It's the sun.
Or sol, Matt.
Or sol. Sol. Yeah, absolutely.
So, Matt, imagine if it needs that gravity, or it would just be a big explosion, wouldn't it?
Yeah, so it's like a massive explosion that's held together with gravity, and it's just perfectly balanced. But the incredible thing about nuclear fusion, that balance, it relies on things like Paul's exclusion principle and stuff like that. It's just outrageous. But But that cloud, that original cloud that you talked about, that's it. 99.86% of that cloud is now this big ball of plasma at the centre of our centre of our solar system.
Do you know what else? You told me to do some research on the sun.
Yes.
Well, you said there that it's a ball. Well, it's almost a perfect sphere. In fact, there's only a 10-kilometre difference in its polar diameter compared to its equatorial diameter. And considering the vast expanse of the sun, this means that it's the closest thing in the observable nature to a perfect sphere. Did you know that?
Do you know what? I really didn't know that. That is incredible, considering it's spinning, and it's
10-kilometre difference. That's amazing, isn't it?
It is outrageous. I mean, it's just unbelievable.
Considering, right? Here's another thing I found out, and I love a stat about size, Matt. How many Earths do you think you could fit inside the sun? And I don't mean if you broke them all down. I just mean taking the Earths as they are and sticking them inside the sun.
Like the sun.
How many could you fit inside?
The sun was a container, and you wanted to put some marbles the size of Earth.
Exactly that.
Don't know. 100,000.
960,000 Earths.
At least I was in the right order of magnitude.
Yeah, you were.
696,000 kilometre radius.
And Matt, I'm going to ask you some questions now. So what temperature do you think it is inside the sun?
I don't know.
15 million degrees Celsius.
Oof. Oh my gosh. Yeah. Yes, that's pretty incredible.
And Matt,
yes.
Here's a true or false. The sun will one day be about the size of Earth.
False.
It's true, Matt. After its red giant phase, the sun will collapse, retaining its enormous mass, but containing the approximate volume of our planet. When this happens, it will be called a white dwarf.
Do you know what? I'm going to go into detail in how the sun dies. Now you've told us how she was born. I'm going to tell you how she dies.
Here we go.
But actually, I want to tell you how the rest of the solar system was born, Jamie, because...
Oh my God, we're going deep today.
We've used up 99.86% of the gas that was available to make the rest of the solar system. So what was left after this thing is spinning. As we know, we've got this massive spinning ball. But just like the arms of your ice skater that you mentioned earlier, imagine that those arms are stretched out and they're spinning as well. And that's now a gas That's a disk. It's become a disk as it's spinning out. So, when you make pizza, you spin it and it flattens out. Exactly the same thing happened with this gas cloud. It flattened out apart from this ball of plasma in the middle. Right. And so you get a disk, and that disk is made of gas and dust, and little tiny eddies in that pick up, and all the dust starts to accrete, make little tiny dust particles bigger and bigger into planetesimals, eventually becoming planets. So the four big gas giants make up 99% of that material. So they sucked up 99% of that material. Everything else, and I mean everything else, all the terrestrial planets, that's Mars, Earth, Venus, Mercury, the dwarf planets, so Ceres, Vesta, Pluto, the moons, the asteroids, all the comets, everything in the Kuiper Belt, everything makes up 0.002% of what was left. 0.002% of what was left. So, Jupiter is 2.5 times more massive than everything else in the solar system combined, if you take out the sun. So, pretty much Jupiter took the most of it. Between Jupiter and Saturn, that's 90% of what was left. So, it's just crazy. In fact, Jupiter's so big.
It's ridiculous.
Jupiter's so big, it's kind of really a binary with the sun, because the sun moves by over a solar radius. Because the point of orbit between the sun and Jupiter is actually lies outside the sun's surface, the barycenter, and so you could consider it a binary in some ways, but the Jupiter would have to become 70 times more massive to do what the sun did, and that's have that nuclear fusion start in the center.
God, my head hurts again.
So and the sun's middle age now, so it's roughly about halfway through. But we live in such a perfect solar system that the sun is just about the right size, so that it's not too small that it's a bit violent and unstable like some red dwarfs are, and it's not too big that it just burns all its nuclear fuel off very, very quickly.
So you say middle age, so it's about what? So we've got 5 or 6 billion years left of the sun?
Yeah, exactly. It's 4 billion years old, and we got about 5 billion left.
Got it. Well, we'll be all right.
It's a G2V star, it's part of the main sequence.
So, Matt, I don't want to bring in religion to the podcast at all.
Yeah.
But I will say this.
Yeah.
People who are religious and believe in a designed universe, did you think that they believe that it's just going to keep going on and on? I know it's a long time away, but, I mean, come on. We're all going to be dust.
Well, possibly
everything's going to be dust.
Well, we've got 5 billion years to sort it out. That's a long time, isn't it? So
imagine someone saying that to you. Right, we've got to sort this out. How long have we got, Gov?
About 5 billion years.
5 billion years.
Oh, do you know how many tons of hydrogen the sun is getting through every second?
Oh God, it's going to be I don't know.
600 million tons of hydrogen going up in nuclear fusion every second. That's 4 million tons of matter converted directly into energy, and that energy is everything that we have, just everything that we have. And
what's that? What's that figure in a year, Matt?
Oh God, it's absolutely huge, isn't it?
It's big, isn't it?
That energy takes 10,000 or up to 170,000 years to go from the core, make its way through the star, and eventually escape the sun as light and heat.
Oh my God!
So do you want to know? Do you want to know how the sun dies?
Oh yeah, definitely.
So we're talking about 5 billion years. So about 5 billion years, the hydrogen fusion is going to run out of hydrogen. And so the hydrogen is diminished to the point where the sun can no longer hold up this massive pressure on it. Hydrostatic equilibrium, it's called.
It sounds like a Muse song, doesn't it?
Yeah, no, don't mention Muse. So the luminosity of the sun will have nearly doubled, and Earth will be brighter than Venus is That's the point where, as you said, the sun will expand into a subgiant phase and slowly double in size over about 500 million years. And then it will expand very rapidly over 1 billion years until it's over 200 times larger than today and a couple of thousand times more luminous. Bye-bye the rocky planets, including Earth.
Well, Matt, when we say bye-bye the rocky planets, how long before that would we just be frazzled? I mean, forgetting being consumed by the sun, but when would we actually, all life just go, okay, we're done?
Consumed by the sun. It might not get consumed by the sun. So Earth's orbit may have drifted away just enough so that the Earth is just outside this outer atmosphere of the sun at that point, I think. So it's really, really close. Of course, it's so bright and hot and right next to us at that point that everything on Earth will be completely fried, even more so than on Mercury. So, but Mercury, Venus, they're gone. They are gone. They're done for. Dead as dodos.
Dead.
So that starts the red giant branch phase. Now, every time I mention these branches, they're to do with these Hertzsprung-Russell diagrams of the Russell that we mentioned earlier on, who worked with Shapley.
Yes.
And those Russell diagrams have been a really, really brilliant way for people to understand how stars work. It's just by looking at all the stars that they can and categorizing them in terms of their brightness and their color, temperature. It's just a brilliant little diagram. So the sun basically makes its way down various branches of this diagram as it changes in its cycle. So now it's on the red giant branch phase, where the sun will spend 1 billion years and lose a third of its mass. So there's at this point, there's an inert helium core surrounded by a shell of hydrogen that's fusing rather than the core. And this inert helium core is just sitting there. And then suddenly, and I mean suddenly, the helium ignites as the helium suddenly goes into nuclear fusion.
Ooh, that sounds dangerous, Matt.
The helium then gets fused into carbon. And 40% of the sun's mass is converted into carbon within minutes. Bearing in mind everything else was taking millions, if not billions of years to happen. And then suddenly we have this enormous event, the helium flash, that happens in minutes, which is crazy, isn't it? And then the sun then shrinks down 10 times its current size, 50 times the brightness, but slightly cooler. And that's known as the red clump phase.
Not as attractive, is it, the red clump?
And then it gets a bit larger, more luminous over the next 100 million years as it burns helium in the core. Then a similar process happens when the helium starts to run out. So the helium starts to run out, just like the hydrogen did. But this time, everything happens a much faster, much larger, and much brighter. So that then enters the asymptotic giant...
Easy for you to say.
branch phase. Easy for me to say. And the sun is alternately burning hydrogen in the shell or helium in a deeper shell. After about 20 million years, the sun just starts to become really unstable, loses loads of mass with thermal pulses, and the thermal pulses become larger each time, and the later pulses pushing the luminosity to as much as 5,000 times the current level.
Damn.
And then the post-asymptotic giant branch evolution is faster. The luminosity stays approximately constant as the temperature increases with the ejected half of the sun's mass becoming ionized into a planetary nebula as the exposed core reaches 30,000 K. Now, I've got a quote from Albert Zylstra of the University of Manchester that says, "What we've shown is that the core will be hot enough in 5 to 10,000 years after the outer layers have been ejected, and that it's quick enough that the sun is just on the lower limit of being able to form a planetary nebula." And of course, planetary nebulas are a beautiful thing. So eventually our star will create this beautiful planetary nebula, like the Cat Eye Nebula or one of those kind of things.
God, that's ridiculous.
Yeah, and then that final naked core, as you rightly said, will become a white dwarf
White
A
dwarf.
white dwarf will have a temperature of 100,000 Kelvin. And you're saying it's about the same volume as the Earth.
Absolutely, that's what they say.
And it will still have almost 50% of the sun's present-day mass.
God, that's ridiculous.
And then 10,000 years after that, the planetary nebula will have dispersed, and the white dwarf will carry on shining a little bit for trillions of years before fading into a black dwarf. Basically, an enormous
Whoa.
black object, massively dense, that you can't even see because it's no longer shining, because there's nothing going on. That point, the universe is a
God
pretty
damn.
depressing place, isn't it?
Matt, is there a video that we could, like a sped up video of all this happening online that we can put up? There must be,
mustn't there? Yeah, let's
try and find
let's
one, because I want to put this into visuals.
Into visuals, I agree.
My God, that is, I can't actually wait to listen to that back, because I mean, that's ridiculous, isn't it, Matt?
Yeah,
I've said that. I've said ridiculous 3 times.
Yeah, the Hertzsprung-Russell diagram's really cool, because the sun kind of, at the moment, it's kind of right in the middle, and it's on this main line of it, and main sequence, it's called. And then it will sort of make its way into these sort of various other parts of the diagram as all these various changes happen to the star. And it's a beautiful representation. It's one of those diagrams that you see all the time because it contains so much information and so much useful information that triggered all this kind of research and the way that the stars work. And even now they're adding rarer and more anomalous examples as more and more stars are analysed and mathematical models considered. And and they add things like quantum mechanics and classical mechanic models to stellar processes. So it's just brilliant.
Well, Matt, we're not going to stop there, are we?
There is a couple of mysteries about the
Here
sun.
we go.
So there's the faint young sun paradox. Do you know this one?
No, I don't.
There's a contradiction here. Is that when the sun first started, it is getting slightly brighter and hotter. So the output would have only been 70% as intense at a certain epoch when there's supposed to be liquid water on Earth. And we know that there was liquid water on Earth. And the real weird thing is how has the sun and the Earth climate balanced to such an amazing degree that we've had water on the planet all the time? And that the climate has been suitable for life, that somehow the sun's output and the conditions on Earth have always been just about right. You could have easily have ended up with a situation where the water froze or the water was boiled off, but it's always balancing out. And so you can't just say it's greenhouse effects, because the greenhouse gases weren't that abundant at the time that we had that this was going on, because they can check that in the geology. So it's not quite it's not solved, this mystery that was first raised by Carl Sagan and George Mullen in 1972. So
Heavyweights.
So yeah, the faint young sun paradox.
Well, there we go. That's the faint young sun paradox. Well, but Matt, have you heard of the coronal heating problem?
I have, but you may tell me about it.
Oh, here we go. It's the temperature of the photosphere. It's approximately 6,000 K, whereas the temperature of the corona reaches 1 million to 2 million K. The high temperature of the corona shows that it's heated by something other than the direct heat conduction from the photosphere. How the sun manages this feat remains one of the greatest unanswered questions in astrophysics, Matt.
Oh, it's crazy. Now, but apparently that was first... The evidence for that was first discovered during an eclipse in the 1800s. So this
really,
so this coronal heating problem has been around for a long time, and of course, that is the reason why they've launched the Parker Solar Probe. It's absolutely its primary purpose is to actually find out what the hell is going on, and it has taken decades and decades of hard work to make this technological feat possible.
We're curious primates, aren't we, Matt?
We really are. I think this is one of the greatest. The fact that we've worked out so much about the sun, yet there's all these other mysteries. But we're so, as apes, we're so brilliant that we've built spacecraft. And this spacecraft this week, the Parker Solar Probe, has become the nearest man-made object to the sun. It's gotten closer than 26 million miles away from the sun.
It's insane.
And it did that October the 29th. And it will almost certainly be now the fastest spacecraft travelling relative to the sun at about over 154,000 miles an hour.
That's quick.
It is quick, and it has to go quick so it doesn't get trapped by the gravity well of the sun, which you can imagine is pretty huge. Its closest approach in 2024 will be 3.83 million miles from the sun's surface. I mean,
jeez,
that is incredible. So it's going to keep doing these loops round. It's got very close on this first loop, but it's going to get closer and closer and closer as it uses Venus to drop down into closer and closer orbits.
Well, I hope its wings aren't made of feathers and wax, Matt. That's all I'm hoping for.
So because it's only 3 million miles away, it's going to be able to analyze these particles rather than us trying to analyze the particles from 93 million miles away. And so we should have a pristine measurement of the corona and try and work out what the absolute hell is going on with the coronal heating problem.
Deuce? Well, there we go.
So that,
blimey.
Yeah, well, I've got news of 2 other NASA spacecraft. Not good news.
Go on.
Kepler is going to get switched off. It's run out of fuel.
Oh.
So it's been flying for 9 years, and it's been in a pretty weird orbit as well. So it's in an Earth trailing orbit, very, very far away. That's it. It's run out of fuel. There's absolutely no way of refueling it, and it's going to get switched off. And of course, it really has been incredible.
It's been great, though.
2,600 planets discovered. I mean, that's just phenomenal.
Amazing.
But luckily, we have TESS, the Transiting Exoplanet Survey Satellite, that was launched recently, and that is going to replace Kepler, and of course James Webb will also be out there soon doing an even more bang out job, we hope.
Jamie bites his fingernails.
But by coincidence, another spacecraft has also ran out of fuel as well, and that's...
You're going to say Dawn, aren't you?
I'm going to say Dawn, and that's spent 11 years orbiting Vesta and Ceres, the large asteroids, or really small planets. Dwarf planets, for God's sake.
Dwarf planets. Matt, have you ever woken up at the crack of dawn?
I haven't. Dawn spacecraft wakes up at the crack of Ceres.
Matt, what's happening with China?
So we've had a first attempt at an orbital launch by a commercial company in China. Unfortunately, it failed. So Landspace, a Beijing startup, its third stage of its Zhuqi-1 rocket that launched from Sichuan Satellite Launch Center in the Gobi Desert failed, unfortunately. So it didn't quite reach orbit. But
unlucky dudes.
Some very good photos from Virgin Orbit as they've attached Launcher 1 to the 747 for the first time in Long Beach, California. So that's really good news. That's looking good. And maybe, Jamie, you and I will go and see it in 2019 or 2020, launching from Cornwall and being the first orbital space launch from Western Europe ever.
I just can't wait. I mean, please let this happen and let it happen next year.
Yeah, it's going to be.
That would really be the best thing.
Absolutely. Jamie, we've had some brilliant emails and some great suggestions, by the way, for future shows. We've got to do one on nuclear propulsion. We've had some brilliant emails about the abominations of bagels as pastry. We've had Jamie, don't mention your breakfasts again. It causes too much upset.
Oh God, I mean, I just couldn't believe it.
And we've had some...
my cinnamon and raisin bagel slammed by our New York listener.
So I loved it.
I still enjoyed the bagel.
Yeah. Shall we finish with some fun space sun facts?
Let's do it.
Here's an interesting one. The sun rotates in the opposite direction to Earth.
Oh.
Sun rotating from west to east instead of east to west, like the Earth.
Is it like in Australia when the toilet flush goes the other way? What's that called?
It's called the Coriolis effect or something. Maybe.
That's it, yeah,
I don't know. I can never remember whether that's an urban myth or not. The sun is travelling at 220 kilometres per second in its orbit around the galactic centre.
That's fast.
And it takes about 250 million years for it to complete one orbit going at that speed. 220 kilometres per second. However, the galaxy itself, the whole Milky Way, is caught in a tug by the Great Attractor. Not Jamie Franklin, another Great Attractor.
It's my kind of tug.
And so we're hurtling towards that, the whole Milky Way, at 370 miles per second. So even faster. But even faster still, the local group, our entire group of galaxies, is moving towards something in the constellation of Hydra, which is pretty scary. And that's going at 600 kilometres a second, or 1.34 million miles per hour.
Oh, whoa.
So add up all those different speeds and God knows how fast we're all moving.
I look forward to the email, Matt, when someone says, oh, well, if we're moving that fast, how come we don't fling off the side of the planet?
But they have got a point.
Well, they have got a point.
How come my hair doesn't move?
To quote an old German colleague of mine, your haircut is like, he's combed his hair with a shotgun.
Nice. Jamie, let's thank our patrons. Thank you very much, patrons. All of you out there that have been helping
bless
with
all
the
our
show.
patrons.
We'll get a proper shout out next week.
Makes us able to do this. It makes us able to continue spouting this absolute nonsense to you. And we thank you from the bottom of our cores.
I've also linked the Patreon to Reddit today. I don't really know what I'm doing there, so bear with us. It's not really done yet. I'm just fiddling around to work out how to kind of get it up and going. So if you've got any suggestions for that, or even if you want to run it, like be my guest. So let me know and let
anyone want to do some admin for us?
Yeah, just dig in. I'm happy to hand over. Something like Reddit. I'm scared of Reddit. It's like you make a comment and then you get like crucified. Anyway, Jamie.
Yeah.
What should people do if they want to help out in other ways?
Well, I'd hop over to iTunes. That'd be my first point of call. Give us a nice review. Because you know what, Matt? It's not just a nice review for our giant egos, and they are bloody giant. They're like red giant egos. It means that people can find the podcast more easy because we go up in the search categories.
Oh, yeah.
So that would be the first thing. And then the next thing I'd do, are you on Instagram like all the cool kids? Why don't you give us a follow? Why don't you give us a like on Facebook? I mean, I'm just saying.
Jamie, I've got an idea, by the way.
Go on.
We both have to post an Instagram picture every day, but we're in competition of who can do the funniest post.
All right.
And our listeners can decide. Just let us know by liking or which one was funnier. I like a bit of competition, Jamie. I think it's healthy.
I like a bit of competition.
It's healthy.
Okay, let's do it.
So over the next month, that's what we'll do.
One a day, okay.
You've been listening to the Interplanetary Podcast. Putting the ace back into space. Thank you very much, Spotcats. You've been marvellous. And I hope you've enjoyed basking in the light of our sun.
Cheers, my little space bagels. Have a good week.
Bye-bye.
Bye.